Today let's focus on learning how the spin qubits work. Let us talk about readout. There are two things I need you to understand if explaining this concept: quantum tunneling and electrochemical potential lines. For quantum tunneling, consider checking out these wonderful videos by Up and Atom and Minute Physics. The critical part here is this. If this is the case of the energy levels in the channel, that is, if this is the potential landscape of a channel, an electron here can tunnel here. Really get this thing right. Imagine these lines. The horizontal ones describe the energy levels, the discrete energy bands of the quantum dot. The lines S and D denote the Fermi energy, that is, the energy of the highest occupied state in the reservoir. You can think of the reservoir as a big bundle of electrons which supplies a quantum dot with electrons. These potential lines are the ladders which can be pushed up or down by the gate voltage. If an electron wants to enter the quantum dot, it has to possess the energy denoted by the line. In this figure, if an electron from the reservoir wishes to enter the quantum dot, we see that this is not possible. This is because the electrochemical potential line is much higher than the Fermi energy. So say we have n electrons in the island, the quantum dot. To add the nth electron, we required n amount of energy. Now we wish to add another electron to the island. This will be the n plus 1th electron, and it will require n plus 1 amount of energy. The energy in the reservoir is in between n and n plus 1. The electron already inside the dot has an energy of n. Thus, the electrons cannot move out of the reservoir, thus blocking out the current. This is called Coulomb Block. Now these lines can be adjusted by changing the voltage of the gate. Doing so, the ladder is brought down so that it lies within the gap. Now the Fermi energy matches the charging energy, that is, the energy required to add or remove the electron from the quantum dot. Readout. This process involves making a spin to charge conversion. In simple words, only if an electron is in a given state, that is, spin up, it can tunnel from one location to the other. A charge sensor, which closely monitors the movement of the electron, detects the change in the charge, thus allowing us to know the state of the qubit. The configuration of our electrochemical potential lines play an important role here. Let us align our potential landscape in the following manner. An electron will tunnel out only if its energy is greater than the Fermi level, that is, if it is in the spin-up state. Thus, there is movement of charge only when the state is spin-up. Detecting this charge, we know a qubit state. Initialization is just the reverse protocol of readout. We can also think of it as the result of a readout process. In initialization, we wish to know the state of a qubit without changing its state, and also we should be able to get many qubits to be in this state easily. Another way to initialize a qubit is to allow it to thermalize to its ground state. But let us consider a more vivid demonstration of the initialization process. For that, let's take an empty dot. The energy of this dot is above the Fermi energy level. Let us subject this quantum dot to a magnetic field that splits the energy level in two levels. The lowest energy level corresponds to the spin down, while the highest energy level spin up. At this stage, only an electron with spin down can tunnel from the reservoir to the island, that is, the quantum dot. If we manage to get the ladder further down, like this, we can ensure that the electron already inside the quantum dot won't tunnel out of it. And until this electron is inside the quantum dot, another electron won't be able to enter the quantum dot. Thus, we see that the electron is initialized to the spin down state. Now that we know how to perform the readout and how to initialize our qubits, let us learn about control and operations on the spin qubits. We control our spin qubits using two things: magnetic fields and electrical excitations. Both of these are used at radio and microwave frequencies. This table describes the effect of the various properties of the frequencies on the qubit. We control the qubit by introducing an alternating magnetic field in a direction perpendicular to the applied magnetic field. This is done by applying an alternating current close to the quantum dot. When the frequency of this alternating magnetic wave is equal to the resonance frequency of the qubit, photons are created with an energy equal to the Zeeman energy of the spin state, and these photons flip the spin state in an alternating manner. That is, the spin starts to rotate as a function of time. These oscillations are called Rabi oscillations, and they form the basis of a single qubit rotation. Spin qubits were initially achieved using gallium arsenide. However, in gallium arsenide, these Rabi oscillations died out due to decoherence caused by the interaction of electrons and nuclear spin in gallium arsenide two-dimensional electron gas through their hyperfine interaction. Every isotope of gallium and arsenide carries a nuclear spin of 3/2. Moreover, these nuclear spins have random directions, thus disallowing the electron to oscillate in the required manner. Their collective effect is known as Overhauser or random nuclear effect. How do we tackle this problem? Simply change your quantum material. Thus, we now use silicon because more than 95% of the naturally occurring silicon carries no nuclear spins in it. We use the isotope silicon-28 because the nuclear spins can largely be eliminated using this isotope. Using this isotope, we can significantly increase the time taken by the qubit to randomize its phase, that is, the randomization time. Now here comes the big question. How do we scale the spin qubits? In order to scale the spin qubits, there are a few requirements. 1. The quantum dots should be uniform and identical. 2. We require 2D arrays of quantum dots. We make use of crossbar technologies to connect the numerous components on the 2D array of quantum dots.